and they actually did the preliminaries pretty quickly. So I thought, this is going well. But then the nurse happened to see me there when they were doing preliminaries and the vitals and stuff, and she said, I hope you're not in any rush today. She said, what time do you need to leave by? I said, I'd love to leave by 12. She said, that's not going to happen. So they were running late, and the appointment was 11:40. I was there for blood work at 10:40. So finally we got away, but I was about a half hour late getting started in my 12 o'clock class. I knew we weren't going to start at 12, but I was hoping to do 12:30 to 12:45. It was like after 1. So we rushed through that, tried to catch up, make up time for that, and then the students had to see me. I rushed over here, so I've been driving all over the place today, too. So enough of my sad, sad song. Okay. Work and energy. Okay. Now, what's the difference in force and work and energy? Is there a difference? Yeah, there must be. They have 2 different chapters of them. Okay. Number 1, force has a direction. Even when you stand on the scales, the earth is pulling you downward. It has a direction. Work and energy, scalar quantities, not vector quantities. So that's one difference. They have different units as well. How about work and energy? Is there a difference there? Actually, they have the same units. They're both scalar quantities. It's just work is the use of energy. Energy is the ability to do work. So they're related to each other extraordinarily closely, even having the same units. So we begin on page, can't even see the page number, 201, and there's little definition of work, or talking about what it is and what it isn't. Work can be done on something, or work can be done by something. This first figure you see here, you're not going to see, that's 8.6. So that is a couple more pages into the chapter. Okay? Sorry, PowerPoint. Sorry about this. Oh. Let me do this. I said I would. Open another screen to do the problems on. Okay, sorry, I forgot to do that. Okay. Let's. Well, now I can't see the. Well, we'll just start from here. Okay. And remind me when we get to 8.6 to open up to that one. All right. There are some common misinterpretations or understanding of work. We talked a lot last time. I can push on the table here. I'm exerting a force on the table, but it's exerting one back on me. It's not moving because it's against the wall. So if I did that for several hours today, pushing on the table, sweating like crazy, getting very tired, I'll put it that way, am I doing any work on the table? No, because the table is not moving. In order to do work, you have to have motion. Okay? So just the force, no matter how hard the force, is not going to constitute work. Even though you might get some pretty hard stares for saying that. For instance, when we bought the house where we currently live, this was many years ago, maybe close to 20, maybe more than 20 now. It was a nice house. It was in the area my wife loved. It had lots of trees. I liked that. It was a nice old house. Fortunately, my wife likes old things. Okay, so anyway, but when I noticed the house had been a certain structure, and then some previous owner had built a room or 2 rooms in the back. But the house was built sort of on the hillside, okay, coming down like this. The area it was built was fairly level, but the front yard fell off this way, the backyard went up this way. So when they put this addition on the back, they sort of dug into the hillside, and it looked squatty. Now that was the looks of it. I wasn't as concerned about that, but I was concerned that the water came down the hill and just went up against the side of the house, because right on the slope. And that's going to create some hydraulic pressure, and I thought we could get some leakage there. Second issue, it looked like they built the wood right up to soil line, or the soil right up to the wood line. And in the South, you don't do this. Why not? Termites. You can easily get termites here in the South. We're warm enough, we get termites are a problem. You go far enough north, they hardly ever have a problem with termites. They don't do termite inspection. That's not a part of things because it's just too cold for them. But here in the South, we do have a problem. You're not supposed to have any wood-to-ground contact. It looked like there may be. So I said to Karen, my wife, when we were looking at it, said, I really like the house. I like a lot of things about it. But, if we do get it, I've got to do something to get the water so it doesn't float against the side of the house. I'm going to have to do some work in the backyard. And I also want to take the soil down to make sure we don't have any wood-to-ground contact. She said, good. I wanted a patio anyway. Whoa here. That's a lot more work than I had planned. I was thinking of a berm and, just do this. I wanted a patio anyway. So it turned out that next summer, it was my first year working at Bessemer State Technical College. That year I had started working there. And that summer I only had, because some enrollment was down some, like it usually is, I only had 2 mini-term math classes the first 5 weeks. We were on quarters back then, 10-week quarters. So I had 2 classes, first mini-term, 5 weeks each, okay? And then, so I was only there 2 days a week. And then the last 5 weeks had no classes at all. So I was home. I was only part-time that summer. So I thought, well, this is the time to get working on digging out the patio. And I won't go into all the detail there, but you can't, anything about the Bessemer-Birmingham area, you can't dig very far before you start hitting rock, okay? And that's exactly what I ran into just about the middle of where the patio was. It was at the edge of the patio, the soil line came up to about here on me, so midway it was right here, like here. And somewhere, actually it was higher than that, about here, because I hadn't gone anywhere down until I hit this rock. And I stepped digging around the rock. I'd hit other rocks that were about like this. I could dig out in a few things with a pick, a shovel, and a wheelbarrow. That's what I was using to dig this thing out. And this one, I just kept digging around, and it just kept going and going and going. Finally, I got it circled. It was bigger than the cross-sectional area that this would cover, and at least that high. And I dug, and I pried, and I cried probably too, but pushed and pulled, but I couldn't budge that rock. And I was sweating, running, all sorts of things. Was I doing any work on the rock? Now, don't tell me that while I'm doing it. No, you're not doing any work. It would have taken a lot of persuasion to tell me I wasn't doing any work, because I felt like I was doing a lot of work, but if I didn't move. So in the everyday sense of the use of the word, yeah, you were working, right? But in the physics sense, no. No work was being done unless you had movement. So they show here this guy. It looks like he has a crate, okay? I'm going to get my pen activated. I'll try to get my pen activated. This system is incredibly slow. It just keeps flashing. There it goes. Okay. So it has a crate on the surface. Okay. And the guy here looks like he's kind of pulling on the crate. Okay. It's a three-dimensional crate, so he's pulling on it, and he's not moving it. Is he doing any work? Exerting a lot of force? Not. Okay? But then either he or somebody else decided, well, let's try pushing on the crate and see if that will get it to move. And this time when he pushes on it, he is able to get it to move. Now he is doing work. Work is done only when you have motion. Okay? Work is done by one object on another object. Okay? That's the concept of work. So here is your basic definition for work, W. And that's a capital W, by the way. If you remember in the last chapter, chapter 5, we talked about little w, which represented weight. Capital W represents work. Okay, so that's the difference here. So capital W, weight, is equal to force times a displacement. Now that may seem like an odd symbol to use for displacement, but this takes the place of x if it's moving this way, y as if it's moving that way, just any displacement. Force times a displacement. Now, the book wrote the F and the S next to each other. I put that center dot representing multiplication. There's a reason for that. Okay? The book isn't focusing on this, but I will for just a moment here. Force is a vector quantity, though we're not going to mess with vectors. I told you that earlier, but it is. The force is. Displacement is a vector quantity. When you're multiplying two vectors together, you can do that one of two ways. The first of these is called a dot product, and that's why I use the dot here. The second is called the cross product. With a dot product, the result is a scalar number. Work is not a vector. It's a scalar. The cross product would produce a vector quantity. That's not what we're doing. And by the way, those two multiplications are very different. You don't have to worry about them, but they are different. Okay? So W is work, F is force, and S is the magnitude of the, well, is the displacement. So writing it the way the book does, it's Fs. Now here's the caveat that you need to do, that you're not mentioning the vector quantity of it. I can push on this spool by pushing this way, by pushing that way, or by pushing that way. Now what did you notice? Okay, when I push this way, almost in the same direction of motion, that's when I'm doing the most work. Because, remember these are vector quantities here, what they mean here, F is the force in the direction of the motion. When I push like this, part of my pushing is into the floor. Okay? That's not doing any work. It's not pushing down any. Only the part of my force that's in the direction of the motion is producing motion. So that's why when they say it in the text, this is the force in the direction of the motion, not the total force, it's the force in the direction of the motion, and then S is the magnitude of the motion. And notice, the same force produced more motion that way, less motion that way, no motion that way, because now the force is perpendicular to motion. There is no force in the direction of the motion, even though I push it, exert a force on the chair. Okay? So that's what force is. Work is. The force in the direction of the motion times the amount of motion. Okay? That's what defines force. Okay? Now, let's think about the units for force. In the SI system, what is force measured in? Say again? Okay, SI system, that's in newtons. Remember Sir Isaac? Displacement is usually measured in SI. We also call that the metric system. Metric stands from the word meter. Earth to class, come in please. Okay, a Newton meter. Okay, and work it has a unit too. You could call it a Newton meter. That would be perfectly fine. You could also call this, because a Newton is a kilogram, that's mass, times acceleration, meter per second squared times meter. This could be a kilogram, meter squared per second squared. That's a unit. That's the fundamental units for work. Kilogram, meter squared per second squared, which could be called a Newton meter. But, and we'll get to him a little bit later, there was a guy who did a lot of the early work on work, and his name was James Prescott Joule. So this, they named the unit of work after him. A joule is a Newton meter. And that joule, by the way, is spelled J-O-U-L-E. That's his name capitalized. The unit is usually not capitalized. This symbol is capitalized, but the unit isn't. That is a joule. Okay? That's the SI unit for work. It's a kilogram meter squared per second squared. Okay. How about if we're doing the U.S. customary system? What would that be? What is force measured in? No, mass is a scalar quantity. Pounds, exactly. So that's a pound. And what is distance measured in, the SI unit? Foot, exactly. Now, we usually don't say pound feet, we say foot pounds. And it doesn't have a special name. So we measure work in the U.S. customary system with the unit of foot pounds. Now, here's the other reason I brought up this thing of dot product versus cross product. Have any of you ever used a wrench? It had a certain strange thing about the handle and stuff. It had a gauge on it, and it was the gauge was measured in foot pounds. Have you? What was that called? You remember the name of the wrench? It's called a torque wrench. Okay? I thought you were nodding yes, that you had. Yeah, okay. That's what it's called, a torque wrench. And guess what? Torque is also measured in foot pounds. But that's different from work. And here's why. Because the other form of vector multiplication, you don't need to know this, I'm just telling you, is force cross displacement. That's called a cross product. And a cross product is measured differently from a dot product. They're both multiplications, but they're different because you have different vectors that you're dealing with. And this is a vector quantity. So torque, and its symbol is a Greek letter tau, and torque is a twisting force. Okay? And probably one of the easiest way to picture this, have any of you watched a car engine with the hood up and someone sitting in the seat revving the car, revving the engine? And if you notice, the engine does this kind of motion. Its torque is trying to pull it out of the thing. That's why they have motor mounts to keep it in place, but they're somewhat flexible so you don't have vibrations, and you see the engine trying to pull its way out. That's torque. Okay? That is a cross product. It's measured in foot-pounds as well because it's force times the displacement. But that's a vector quantity. And torque is always perpendicular to, you use the right-hand rule. If the force is this way, the displacement that way, the torque is this way. Whereas there, and if you think about your wrench, okay, you're pushing this way, your displacement from the nut that you're trying to loose is that way, so those are perpendicular to each other. That's where you get your maximum torque, and the torque is upward. Okay, force times displacement is a vector quantity. This force in the same direction has no torque because it's in the same direction. So this is a foot-pound that's a scalar quantity. So you don't need to know the torque part, but don't confuse the foot-pounds of work with the foot-pounds of torque. They use the same units, but they're completely different quantities because the forces are perpendicular with torque, parallel with work. Okay, let's do example 1. So I'll erase all this, including, unfortunately, the formulas, but hopefully you got them. So let's do it. Find the amount of work, so that's what we're looking for, work, there's your unknown, done by a worker lifting 225 newtons of bricks. 225 newtons of bricks. What's that a measure of? What do we measure in newtons? Second? Force. Okay, that's the force applied. He's lifting 225 newtons of bricks to a height of 1.75 meters. Okay, they're told there that's your height, which you could also call your displacement. This time it's lifted upward. He picked them up and lifted them, put them on his shoulders. And that's about right, because most men's waist is about 1 meter, and then up to here would be about another 3/4 of a meter. So he's lifted it 1.75 meters. So how much work did he do? It's 225 times 1.75, and what does that give you, said? Okay, wait, let me get it written in here. Newton times 1.75. I forgot to put this in meters. You let me get away with that. And say it again, 3 what? 393.75. Is that what I heard right? And that would be Newton meters. But you only have 3 digits coming in here, 3 digits coming in here. So what must you have here? 394. And what's another unit for Newton meters? Joules. Okay. Thinking of a diamond. No, never mind. Okay. 394 joules. Three digits, yes. Round it, however you round, up or down, yes, exactly. Okay, that's when you follow your rule. And what the rule is for rounding, just in case you've forgotten, you have 3 digits here, 3 digits there, so when you get your answer, start from the left and count 1, 2, 3 digits. This is the one you need to determine. You look to the right, if that next digit to the right is 5 or greater, go up. If it's 4 or less, leave it alone. Leave that 393. Okay? So you count the number of digits you're going to keep, look to the right, and that determines whether you increase it or leave it the same. Good question. All right. Here's example 2. A worker pushes a 350-pound cart a distance of 30 feet. So, I think I'll erase the one before. Is that okay? Now, I didn't draw the picture. Hopefully you got your books and you can see the picture. It just takes me too long to draw them, and they're so ugly you laugh at me anyway. I mean, they're so ugly I don't want to do them anyway. Okay? So here the worker pushes a 350-pound cart. Now, the way that reads, what's that 350 pounds? Second? Okay, it is a force, but what force is that? That's its weight. Okay? Okay, that's its weight. A distance of, so here's your distance, which is also your S, your displacement, of 30 feet. Now here they put a bar over the 0 indicating that's your significant digit, 2. They didn't put a bar over that 0, meaning that one's not significant. So you have 2 digits here, 2 digits there. Okay? By exerting a constant force, so here's your force of 40 pounds. And there they put a line over that 0 as well, as shown in the figure. Now, I'm going to kind of draw the figure. I'm going to make it stick figure. Here's the guy pushing on the cart. Here's the handle of the cart. Okay. And here's the cart. There's the wheels. Okay. He's pushing on the cart. Okay. and the weight of the car is this way. That's your 350 pounds. That is a force, but that's your weight force, okay? He exerts a force in that direction of 40 pounds. And he pushes it a distance of 30 feet, right? Yeah. Okay? Okay. Does that 350 pounds come into this picture at all? No, because that's perpendicular to the force. Perpendicular forces do not do any work. It's only the parallel force, and that's the 40 pounds he's pushing. You see, the ground is pushing up on the cart with 350 pounds too. So he's not having to lift the cart. If he was, he's doing a lot of work. He's just pushing the cart, okay? For instance, I'm going to lift the chair, okay? That's more force than it takes me to push the chair, okay? So I push with something a lot less than what I lifted. So that 350 is perpendicular to the direction of motion. That's not in play at all, okay? Now, there is a sense that is a little bit, because when I push on this, you hear it making noise on the floor. That's because there's friction with the floor. The friction depends on the weight of the chair. So it has got something to do with it because it contributes to the frictional force. That's resisting my push, okay? Then if you were to sit on the chair and I try to grab, there's a lot more resistance because there's a lot more weight down, but that's not the same. And he's pushing on this with wheels, so that's going to make it even easier to do. But he still has to exert a force. So what work is he doing? This is weight. The work is what? Force times displacement, and that's going to be, okay, 40 pounds, that's the force, times 30 feet, and then we reverse the order of it, and what does that give us? 1,200 foot-pounds. And there is no special unit in the U.S. customary system. We just use foot-pounds. Now, should I put a bar over either of those two zeros? What you think? Sure. No, because you have 2 digits here, 2 digits there. I should have put bars over these. And we only need 2 digits here. The 1, 2 is the 2 zeros are not significant digits. So we don't put that. So that's a pretty interesting problem, because the 350 pounds is a force downward, doesn't contribute to the work being done. Now, this is not what they intend, but I'm going to ask you anyway. What if you were pushing this up a ramp? Now, the 350 pounds is in this direction. Part of that force you're having to overcome. And it's harder to push that same car up a ramp than it is on a flat. So then, part of that, the component of the force, here's the weight downward. It has one component up the ramp and one component perpendicular to the ramp. This one's not doing any work. This one is. You're having to do work against that one. And on the other hand, what if it's going down a ramp? He may actually be holding back, because then the cart's going to tend to roll down. So you see, the weight could play, but when it's perpendicular, no contribution at all. Only when a component of the force is in the direction of the displacement. That was no extra charge. They didn't do that in the book. Okay. And we got 1,200 foot-pounds just like they did. Now I like to put a little dot in between foot-pounds. They like to just leave a space. That's completely up to them. Okay. Now, what if the force was not in the direction of the displacement? Okay? Then we have to deal, and this is where that slide comes into play. So let's see, how do I do this? Okay, discharge that and go back to this. Not there, this. Ah, here we go. Now we'll go to this slide. All right, finally. Now, have y'all, any of you, ever had any trigonometry? High school, anytime, a little bit? Been a long time or never? Never. Huh? Long time. Okay. Let me go over just a few simple things about trigonometry. All trigonometry is using ratios to your advantage. Okay? Now, what's required, not absolutely required, but what makes it easier if you only deal with right triangles. Okay? Now, this is showing me pulling the chair like this. Okay. Now, my effort, the force is this way. The displacement is this way. So it's only the portion of the force that's in this direction that's contributing. The force up here is not contributing, except in the fact that it's pulling it off the ground and making friction less. But we're not going to get into that now. Okay? This would be like if you're pulling this box. It's the only part doing work on the box is this component in this direction. So here we have a right triangle. Okay? I'll use those things here. Okay, here is the total force I'm pulling. That's a vector quantity. The magnitude of that is proportional to how much force it is. If that was 50 pounds, it could be that. 100 pounds would be that. 25 pounds would be that. Yeah. So the magnitude is represented by the wing. Okay? However, it's only the horizontal component of that force. It also has a vertical component, and that makes your right triangle. You're always going to have the right triangle there, horizontal perpendicular. Okay? And it doesn't also have to be horizontal. It's the component in the direction of the motion, which is going to be this way, and the component perpendicular to the motion, which is that way. So it's saying the same thing. Okay, now with right triangles, we name these three sides. Here's the right angle. So the longest side is always called the, anyone know? Hypotenuse, exactly. This side, and here's the angle, theta, this side is called the adjacent side. It's the one adjacent to the angle. Okay? This side over here is not part of the angle, so it's called the opposite side. Okay? So let's think in those terms. This is the hypotenuse. Well, let me get my pen back. Okay? This is the hypotenuse, this is the opposite, and this is the adjacent. Okay? Now, the trig functions relate to these three sides of the triangle. And here's how they relate. The sine of that angle, theta, is the opposite side over the hypotenuse. The cosine of that angle, theta, is the adjacent side over the hypotenuse. And the tangent of that angle, theta, is equal to the opposite side over the adjacent side. Now, there's three more, but we seldom use those. So I'm not even going to get into that. These are your three basic trig functions. They always relate to right triangles, and they always relate this way. The side opposite the right angle is always the hypotenuse. That's always the longest side. And then the other two, the one opposite the angle is the opposite side, adjacent to the angle is the adjacent side. Okay? Certainly the hypotenuse is adjacent too, but you've already named them. Now, you want the easy way to remember this. I'm going to give you three different ways. The first one, I don't find that easy, but a roommate I had in college, he just loved it. He said, and I've seen it in other places too, so it wasn't just him. He said, Tha, Ka, Toa. Well, I can't tell the difference between Psi and Ka, which is A and which is O. So I don't like that one too much. But the very first time I taught trigonometry, I think it was the first time, maybe the second, at Bessemer State Technical College, okay, I had a student in my class that said this one. Oh, that's some old hag caught another hag taking oats away. And that was pretty easy to remember, except I really don't care for hags, okay, but it was just something. Well, then, about 2 or 3 times later when I taught trig, another student said, oh, that's, I like this one better, some old hen caught another hen taking oats away. I like hens better than hags, okay, so I usually go by that. That's the easy way to remember. It's always a ratio, and that's what we've got. Now, so here we are dealing with, there's your force you applied. Here's the force in the direction of your displacement. Which one of those relates the hypotenuse to the adjacent side? Look at it. Which one does hypotenuse and adjacent? It's called another hen, isn't it? Cosine. So, here's what we can say, and we can say it any way you want to. Where did that happen? Okay. All right. You can say that the cosine of the angle theta is equal to the adjacent side, that's f sub x, over the hypotenuse, which is f. So if we want to know what f of x is, you know what the force is. You want to know the force in the direction of the displacement. Multiply both sides by that force. Okay? The forces cancel out, and you have f sub x is equal to f times the cosine of theta. Okay? Now, do any of you have calculators you use in the course when you're doing your tests and things like this? Okay? Do you have the trig functions on them? If you have the little cheapy calculators, they probably don't. That one, I'm sure, has a trig function on it. Or is that your telephone? That's your telephone. Yeah, a smartphone. Okay. Now, let me tell you about smartphones. So yours will have it. About smartphones, when you hold it upright and go to calculator mode, you won't see a trig function on it. Turn it this way, though, landscape. Do you know how to get to your calculator? All right, you're on it, okay? You turn your phone like this, and there you get sine. Okay? Does everybody see that? When you do your calculator upright, you're getting a cheapy calculator. Just add, subtract, multiply, divide. If you turn it this way, you get a lot more functions. Okay? So, now you have to learn to use it with that, and it has certain syntax that you have to do. So this is, now, and here's the deal, folks. You know how much force you're applying. You know the F. You know the angle here. You can measure it somehow. What you don't know is how much of that force is in this direction. And this is the formula that gives it to you. You know this, you know this. You can calculate cosine of that angle theta, and then you get the force in that direction. That's the one that you multiply by your displacement, the F sub x, not the F. Okay, because it's only the component in the direction of your displacement. Okay? I think this is example 3. Okay? Okay, let me write down what I just said because I have it in the book. Okay? Now, what they have in the book, and there's a reason for this, they put bars here. Now, the reason they put the bars is because their forces are, if you'll see that, they're bold. That means they're vectors. See, I can't write bold, so I put the little arrow over it. So if I were doing this, I would do. So there's, if I were writing that correctly, then that would be F sub x is equal to F cosine theta, because cosine theta is F sub x over F and multiply both sides by F. So if I put those over it, we're not interested in the vector so much. We're interested in the magnitude of the vector, and that's what the bars stand for. That takes just the length of the vector, not the direction. Okay? But you have to deal with that. Okay? So, what is your work then? The work done by pulling. You're pulling it. See, that's a rope tied to the box. You're pulling in that direction. What is the work done? The work done is not F times distance. They didn't show the distance. Here is the displacement. Okay? Actually, they use that. Okay? It's not F times S because F and S are not in the same direction. It's F sub X times S. F sub X times S. And these, again, are magnitudes. Okay? Not vectors. The displacement is a vector, and that's just the magnitudes. And what that is, F sub X, is F, magnitude of F times the cosine of the angle theta, which you can measure, times your displacement, S. Magnitude of S, if you want to be technical about it. So it's Fs cosine theta. That's what they're going to use without putting the bold. In fact, writing it in italics, they do L work is equal to Fs cosine theta. They just brought the S over next to the F. You can put them in any order you want. Okay? So work W, capital W, is the work done. F is the force done. Applied force, that you can measure. And then S is the displacement, and the theta is the angle between the applied force and the direction of motion. All right. Got it? Okay. Let's go to this problem. A person pulls a sled along level ground. See, he's not going uphill or downhill, so that's going to keep it level. A distance of 15 meters. So he goes from here to there, and this is 15, I think it's 0.0, yeah, 0.0 meters. Okay, that's how far he's going to pull the sled. Okay? By exerting a constant force of 215 newtons. That's the force. Okay? That's the vector quantity force, 215 newtons, at an angle of 30 degrees, 30.0 degrees, and that's your theta. Okay? And by the way, theta is a Greek letter also. It's kind of corresponding to, I don't know, it doesn't correspond to anything in the English alphabet. Tau corresponds to T. Theta doesn't have a correspondence. It's just somewhere in the Greek alphabet. Okay? With the ground, how much work does she do? Oh, this person is a she. Okay? At 215 newtons, but the angle is 30.0 degrees. How much work does she do? So you tell me. We're looking for work. You can either do it 2 steps, piecing all the information together, or you can use the formula that pieced it all together and come up with the answer. How do you want to do it?
So if we do 215 multiply.
Okay. What would you multiply?
Multiply the force.
The F force? Mm-hmm. Okay, F times S, there's your displacement S, times the cosine of the angle theta, and that would be 30.0. I should have put theta in here, but degrees. So this will be 215 newtons times S is 15.0 meters times the cosine of 30 degrees. I'll write that down, cosine 30.0 degrees. All right. Now, guarantee you when you put this in your calculator, it's going to come up big, long number of digits. Okay? Do you know how to put that in your calculator? You don't. Okay. I'm not sure you do because I think the iPhones or smartphones have a special syntax. I think you put in the angle first and then the cosine. Okay. So let me, yeah. Now, also on your smartphones, somewhere you'll see the symbols, somewhere there, I think, DEG or RAD. Do y'all see that on your smartphones? DEG or RAD? Okay. Which does it say for you? Okay. Get out of RAD. Because this is measured in degrees, not radians. So if you use say again? Okay, as you see DEG. Be sure you're in the right mode. And this was given you in degrees, so get in degree mode. Don't be in radian mode, you're going to get totally wrong answers, okay? You might even get negatives, and how could that be the case? Okay? Okay, and generally if you're using your phones, you have to enter the degrees first, then press the cosine. Okay? If you're using a calculator, a good calculator, you can enter it just like you're reading it. If you have an old scientific calculator, you have to enter degrees first and then the trig function. Okay? You have to know your calculator. Are you having trouble with yours? What's that? Okay, now notice here, you're in radians. Oh, I see. Okay, so now you're in degrees. Okay, so now you enter 215 times 15 times, okay, 30. That's not the right answer. What is it? Pretty close, isn't it? Okay. And here's why. Significant digits. Read how many significant digits. How many significant digits? Okay, when you run this, 1, 2, 3, look to the right, it's less than, whoops, I just got rid of it. It's less than 4, so you can't do it. You round down if it's less than 4. All right. Okay. You know it's the right answer. But you see, three significant digits, so you count 1, 2, 3 digits, look to the right, so you change that to 2,790. It's all that. Yep. Okay, you got 3 digits, 3 digits, 3 digits, everything on here. So you got 1, 2, 3, look to the right, it's a 2, then it's a 0. If it was a 5, move it up to 8, and then the 0 would be 2. Okay? Okay, you're in radian mode though. Okay, now you're in degree mode. Okay. Times. Okay. Now, you enter the degrees first. That's 30. Okay. Then cosine. Then theta. Okay. You count 3 digits. 1, 2, 3. Look to the right. It's a 2. That's less than 5. Change that to 0. Yeah. You
So
only
it
got.
won't be just 279, 3 digits. You just have to put 0.
No, you count 3 digits. 279. Then look to the right. That's a 2. It's less than 5. Drop.
Now, if it was over 5,
then you do 280 and you put a line over the 0 there. It moves it up. Okay? Everybody got it? All right, good deal. All right. This is all fun, isn't it? All right. Good deal. All right, we got Juan and Sonia, okay? Oh boy. Okay. So let's get out of that one for a moment and go to, this is such a pain in the neck to do. I think, is that the one I want? I can't tell. Nope, it's not. Is this the one I want? I think so. Yes. Okay. Let's go back to this one. All right. Juan and Sonia use a push mower to mow the lawn. Eager beavers they are. Juan, who is taller, pushes with a constant force of 33.1 newtons on the handle at an angle of 55 degrees from the ground. So here is his picture. We're not going to draw one. We're just on. Whoa, let me get my pen back. Okay. So here's the ground, and fortunately they're on flat level ground. They don't live in Birmingham, do they? Okay, he's pushing down with a force of 33.1 newtons. Okay? His angle he's making here is 55.0 degrees. Okay? Sonia, who is shorter, pushes with a constant force of 23.2 newtons. So here's level ground. So one didn't give her the, so this is one. Here is Sonia. Okay? She's pushing down, because she's shorter, at 35.0 degrees. And her force is down this way, and that she's only pushing with 23.2 newtons. Okay? With the hand on the handle with a at an angle of 35.0 degrees. Assume they each push the mower 3,000 meters. So they're pushing it 3,000 meters, both of them. Now, interesting what they put a line over the second zero, the middle zero. How many significant digits is that? 3. 3 up there, 3 there, 3 there, everywhere 3. Okay? So what is who does more work and by how much? So how are you going to find out the work done by one? $33.1 Newton times by what? Which is 3,000 meters times the cosine of 55.0 degrees. Okay, that's the work done by one. What's the work done by Sonia? 23.2 newtons times same 3,000 meters times the cosine of 35.0 degrees. That's ugly writing, but hopefully you can follow. Okay? When you get one's work, tell me what it is. Okay, say that again. One more time. Huh? Okay. 575. What was that unit?
557 and 30.
Oh. Okay, wait. Okay. Oh, I hit the wrong thing. Okay. That was Newton. Okay, 57 with 3 zeros. 0, 0, 0. Wow. And what?
The line goes the first 0 is 3
Exactly. Now that came out an exact measure like that? No, I didn't think so. Oh.
It came out 56,956.
Okay, say that again.
56,956.
956? Okay, yeah, so you did it right. Absolutely. Way to go. Okay, and what units? Newton meter, which would also be a joule. Now, since that's such a big number, you can shorten the number since this is SI and call it 57.0 kilojoules, because kilo means 1,000. So instead of the 57,000, make it 57 kilojoules. But you need the extra zero there indicating significance. Okay, let's do the work done. Yeah.
Would you accept if you doing it the other way, the 579?
I don't care which way you do it. It's just to match the answer in the back or whatever. Just recognize those are the same answers. Okay? Sometimes I don't like writing just tons of zeros out there, so I like to use a unit to do the work for me. Okay? I'm lazy. Okay? And by the way, to be good, I think in science and math, you have to be a little lazy. Always finding the easiest way to do a problem, right? Okay. So, if you're a hard worker, you can still do it. That's all right. Okay. So this is the work done by 1. Let's do the work done by Sonia. What would that be? 5, 7, 1, 2. Okay. Okay. Wow. Okay, they're that close, huh? Now, by significant digits, they did the same work. In reality, she did just a little bit more work, okay? Let's see how they're going to do it. They say the working, oh wait, I'm sorry. They do the same amount of work, however, one must exert more energy because he pushes into the ground more than Sonia, who pushes more in the direction of motion. Now that sounds like it's contradictory, but then too, he is exerting 33.1 newtons of force. She's only exerting 23.2 newtons of force. They're doing the same work, but he is using more energy. Some of his energy is being wasted. Now, some of hers is too. She's pushing into the ground too, but less so than he was. So they're right there, but they say they do the same amount of work. In reality, without the rounding, she does just a tad bit more, but it's really not enough to count, okay? Good deal. Interesting problem, okay? Everybody get that? Anyone need some help with it? Okay, so I notice on your phones then, it's what is set up here, that's what unit you're in, not the button you push. When you push the button, that changes. If you see nothing up there, that means you're in degrees. If you see RAD up there, that means you're in radians. Okay. I didn't know how your phones work, but that's how they seem like they work too. What's that?
I got totally different answers
For that one? Okay.
because my RAD was
At the top, yeah, okay. You got to push the button. It's the RAD.
See, when I first did it, it was in like
Oh, okay. Yours is a different display. That's in radian mode, so when you press that, now you're in degree mode. No, you're not. You're in radian, so they
that's
go
what I
back.
was thinking.
Yeah, yeah. That's what you look at. Yeah. If you don't see anything up there, you're in degrees. On a regular calculator. You got one? Okay. Okay, can I show it here? Okay. See down at the bottom it says DET. Okay, now if you're trying to switch them, you can hit this button here, and then you indicate I want radians. So you go to that one and hit enter, and now it says RAD. Degrees. So you want it the other way, so you hit the RG, and that gives you the option to go back to degree or enter and then DET. Okay. Now some calculators don't have that printed at the bottom, and you actually have to go into it's the big fancy graphing calculator. You have to enter the mode every time and see what it's in, because they don't print it on the calculator. If those that have it on the screen, they make it easy. Okay, you got it. Okay. Any questions? You have a graphing calculator, don't you? Does it show it on the screen? Yeah, but you have to go to mode and pick out the one. Okay. Let me show you that one too. Okay. Okay. Now, see on this one, you don't see anything. So what you have to do is go to the mode key, and then you have all these choices. You're into the gradient of degree, and you've got to see. I know. You can draw graphs with this, and that's what you do. When you go down here, if you want radians, then you go back. Well, you're on radians, so you press enter, and now you're in radians. If you want a degree, you go over here, and you get press enter, and now you're in degrees. But see, when you see your screen, you don't have the DDG on it. And there may be other calculators that do it differently. Just like your display on your phone is different from her display on that phone. But they both have it somewhere. They have the RAD, or if they have nothing, you're in degree mode. Okay. I can tell you're sick about being here, aren't you? Okay. All right. Let's go to, let's clear that off the screen and go to example 5. Find the amount of work done. So what we're looking for again is work, okay, done in vertically lifting a steel beam with a mass of 750 kilograms. So here they give you mass of 750 kilograms, okay, at a uniform speed, a distance of 45 meters. Now your distance there, you could call it Y because it's going upward, or you could call it S because that goes any direction. And that S is 45 meters up. Okay? Can you determine the weight given that information? Anyone want to say again? Yes. Okay, actually you can. Uh-oh. SpaghettiOs. That means we have to remember what we did in the last chapter? Yes, that's what we have to do. You have to get from mass to weight or force. And how do you get that? Say again? Okay, and how did that help you? Okay, a force, and we call that the force due to weight is equal to mass times, second, the acceleration due to gravity. And that mass was 750 kilograms. And what was the acceleration due to gravity? In the SI units, 9.80, wasn't it? Meters per second squared. That's an acceleration. And that will now give you your force, or your weight, or your force, and you multiply that by your displacement. So your weight would be mgs, or mgh, we'll often call it. It's mg is your weight, is your force, that's how much you have to do, and s is your displacement. I like to call it h for height. Okay, that's a lot handier. So it's just that's these, multiply that by your displacement s, and that gives you work. So yeah. Okay. No. Okay. Okay. You like the triangle? No. Which you like? Okay. 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 You're looking for force due to weight, and that's mass times acceleration due to gravity. Yeah, on the bottom you put 750 kilograms times 9.80 meters per second squared, and that will give you force of equal to whatever that comes out to. Okay, no, then you multiply that, and you see you can use the same thing up here. If you do weight is equal to force times displacement, then work. So I say weight. Put the work up here, force here, displacement here, and you can either draw your triangle or draw your circle, and that be your multiplication symbol. So you can use it the same way there too. But do the force first in its little triangle, then do the work in its little triangle. If you're using triangles. You don't have to use triangles, but if you are, do them separately. This then is your force due to weight. Okay? Okay? So do the two-step if you like the two-step, or do it all in one step if you want to do it like I did at the top. Some people like the Texas two-step, so go with that. As long as you don't step on my toes, I'll be okay with it. Anyone get an answer yet? Huh? I believe so. 750 is a big number, 45 is a big number, and 9.8 is a pretty good sized number. So I'd say this is going to be a big number. What do you get? 330,000? Okay. 750? Okay. Now, we got 3 digits here. Let me see. I didn't write down right. Oh, I only got 2 digits here. And here we got 3, so we got to round to two digits. So count 1, 2, 33. Look to the right. That's a 0. Leave it a 0. And now rather than 1,000, let's just write kilo what? What's torque measured in? Say again? Joules! Okay, those are my diamonds, right? Okay. Because you said 330,750?
Because we had this 750 was 3, and the 9.8 was 3 numbers.
Okay, but 45 only had 2 numbers.
Okay.
So they only used 2 digits. So that other 0, you don't put a line over it.
Oh, even so, we're going to disregard the 3 at the bottom. I mean, those other 3 numbers.
Yeah, you just count the first 2 significant, and then look to the right. It's a 0. Leave the 0 alone, and then put kilojoule. If you didn't want to put kilo, then it would be 330,000 joules, or Newton meters. You just put zeros for all the rest of them. They're not significant, because you only have 2 significant digits. Okay? Now, here's another way they did it. Okay? They did 3.3 times 10 to the, how many digits you move the decimal? Here's the decimal there. You move it 1, 2, 3, 4, 5 times 10 to the 5 joules. That's how they did their answer. Okay? A joule is a Newton meter. Okay? Don't let the units and the digits get in your way. Do the problem and do your best with the other. If you got it wrong, I'll show you where you got it wrong, but I don't count off for it. Now, if you got 33 and that's not 330,000, yeah, that's not going to be the same. But if you put 3, if you put all those digits there, I'll just cross them out and put zeros in the place. But I won't count it wrong. Okay. Homework exercises. Now, if I'm remembering right, only the odds are in the back, right? So do number 1, and then any of the odds 7 through 13, as many of those as you like. See, 13 uses the figure. Then you can do 15, and any of the odds 17 to 23. So you choose any of those that you're interested in doing. All right. Now, next time we'll start with power, and don't forget my illustration of digging out my patio. We're going to use that too when we talk about power. Okay?
When did test do?
What's that? Oh, a week from whenever, a week from today. If you need more time, you can have it. Just get it into me before we finish chapter 8. Sooner you get it into me, the sooner I can give them back to everybody. But I haven't got any of them in yet, so. Yeah. All right. Any questions? Unfortunately, we just about run out of time, did we? I hate being a banker, coming in late and leaving early, but I guess that's all we can do today. Okay. Yeah. Okay.
got stuff.
Okay. Yeah, you could have asked that in front of everybody earlier, but they all may have this question.
Oh, I get well.
Yeah.
I was trying to decide the formula for number 7.
Formula for number 7. What do we have there? I'm still recording, so y'all can listen later if you want to. A small railroad engine, is that right, is able to exert a 17,500 pound pulling force. So it's pulling this little engine that could, pulling with 17,500 pounds. The coefficient of friction for steel wheels on steel rail is 0.40. Okay? How many rail cars weighing 45,000 pounds each can this engine pull on a level track? That is a totally ridiculous problem. Now I remember this. And I'm glad you asked. And now I've got to look it up because they've got something wrong in the problem. I tried to check this. I was thinking the first test was okay. But now that you say that, I know it isn't. Let me see if I can find. Second? You got what? Okay. I remember it now. Now, what I think they meant on that one is 4,500 pounds each, not 45,000. Okay, this is test 1, and I apologize for this. It's a sorry PowerPoint and even worse test bank. These came straight out of the test bank, and I didn't find this error until then. I forgot to mark it on my master. But let me see if that works. Right. Okay. Okay. Let me put this in its place. Okay. This is chapter 5.
So did you do the coefficient? Which I don't know is right, but it can't seem like it is. Where does the 0.4? That's the question.
Okay, that's the one. I was working with it, but I wasn't
Sure.
sure.
Yeah, that's why I was like, I don't know if
phase
that's one. So yeah, I did write that down. I was
Okay.
like, no.
I don't have my calculator with me. Okay. Okay. Let me. I may have told you wrong. Let me check this. Okay.
Yeah, and 9 was another one. Yeah, 9.
Oh, I added like the 64.5 kilograms plus 129 kilograms minus 34.0.
The sum of force.
I don't know this one. I was
Well,
just,
but that was the
see, that's what their class was gonna be. So which one was that I was here last week? That's all.
Yeah. Okay. That works if you put the 4,500.
So with the 4,500.
Yeah. But did you use this formula here? Okay. Okay. No, you have to use this one.
Okay, in order for the work.
Okay, this is your frictional force formula.
Okay, that's the
Okay.
one I thought.
Right. It's on page
So, but which one of them is
132.
disregarded?
huh?
We have to use all the numbers that's in there?
Okay. But put 4,500, not 45,000. If you
And
do
use
that
formula.
and that formula.
Okay.
See, this formula
It's 432, you said?
on page 132, that one in the green block, okay, that gives you the force due to friction. See, you're not pulling the weight of the car, you're pulling against the frictional force. This is the frictional force of the car, but you have to use the 4,500 times the 0.4, that's your coefficient of friction, okay? Yeah, and then you divide the number you get there into what your engine can pull, which is 17,500. 0.4, yeah. And that gives you the force of friction for each car, and then divide that into the engine and see how many cars you can pull. Now, in this case, you don't round up. Because what if I said, you can lift 150 pounds, okay? And then I said, I'm going to stack bricks here that weigh 60 pounds each, okay? How many can you lift? Well, 150 divided by 60 is, okay, so how many bricks can you lift? You can't lift 3. So even though that may round up to 3, don't round up to 3. You can only lift 2. Same thing here. You can only pull so many cars, but even though that decimal may be greater than 5, you can't pull another. You round up, that's more than you can pull. Yeah, okay. Yeah. Okay. But the question is, how many cars can he pull? Are you going to cut off and make 0.72 cars or whatever? No. 9, that's all it can pull. This one you don't round, you always round down to the number of cars. If that was 9.9 cars, you can still only pull 9. You can't pull a 10th car. Okay, 9. Okay, let me see if... All right. Okay, 9 I think is right. Right. No, start with your 17,500. Divide that by 1,800. Yeah.
Yeah, that's what it is. After the answer was 1,800 to calculate, I would have hit the divide by 17.
No, yeah. You take the big number divided by the smaller, yeah.
That's always. So
well, not always, but in this problem it is.
See, that would be confusing.
Okay, but wait, think about it. The engine can pull with a force of 17,500, and each car has a frictional force of 1,800. So you can pull more than a car. If you do 1,800 divided by 17,000, you're going to get a fraction of a car. He can pull way more than one car.
So we just do 9 and don't round
Do
up.
what makes it, yeah, and don't round up. You're exactly right. Right, okay. Though I'm not telling you the answer. Okay, now. Was the question about 9? Okay. A 64.5 kilogram person steps off a 129 kilogram rowboat with a force of 34.0 newtons. What is the force that is applied to the person by the rowboat? Okay. Now, on problems like this, draw pictures. Okay? Pictures are worth thousands of words. No, okay, you might use that too, but draw you a picture, okay? Here we have, okay, here's the water, here's the dock in the water, here's the rowboat, okay, and here's the person. Okay, now, the person is 64.5 kilograms. What's that a measure of? What do we use to measure kilogram? I mean, what? Mass. That's the mass of the person. That's the mass of the person. Okay? He steps off the, and by the way, the mass of the rowboat, this is mass of the person, this is mass of the rowboat, is 129 kilograms. Okay? Now he steps off the rowboat with a force of 34.0 newtons. Now I'm assuming that he is stepping off this way with 34.0 newtons. Okay? Yeah. Okay? Now, what is the force? And that's the force he's applying on the rowboat. Okay, right? Now, what is the force that is applied to the person by the rowboat? Okay. Okay, wait. Okay. 5.6. That's on page 138. We were just told the person pushes against the rowboat with a force of 34.0 newtons. Then the question says, what is the force that applied to the person by the rowboat?
So do you subtract masses?
No.
You multiply first.
No. Okay, think. What does it say on page 138? For every force applied by an object A to object B, that's your action, that's the person as A to the object B, which is a rowboat, there is an equal but opposite force exerted by object B, the rowboat, to object A, the person.
So it would be 34.0 minus?
Yes, the opposite direction, negative 34.0. You don't use their masses at all. No, it's just using, negative. Okay, sorry, I wish I could make it harder, but I can't figure it out. You have to put, yeah.
And see, I wasn't here when y'all went over there, so that's why I'm like, all of that is just.
Yeah.
I got a couple more questions.
Okay.
Okay, number 3 and number 5.
Number 3.
Yes, sir.
Okay, let me just check here. All right, good. Okay, now number 5, I think, may potentially have a problem too. I had to write something down for that one, so I have to check on that. Okay. All right. Number 3 first. The coefficient of sliding friction, that's also kinetic friction, by the way, on concrete is 0.30. What is the weight of steel? What weight of steel can be pulled across a concrete floor by a winch with a 450-pound capacity? Okay. Now again, I like to draw. Huh? I like to draw pictures. Okay. I don't draw well. Okay. So here we have the concrete floor. Okay. and the coefficient of sliding or kinetic friction is 0.30. Okay, and that the first 0 is just a placeholder. The last 0 is significant, so that's 2 significant digits. Okay, what is the weight of steel? What weight of steel can be pulled across the concrete floor by a winch with 450-pound capacity? So here's your winch over here, and I'll just draw, here's a winch. And you're pulling this cable, and here is the steel, okay? And this steel is, you're looking for the weight. The weight of the steel, that's your unknown here, okay? Now, this has a pulling capacity of 450 pounds. So this can pull 450 pounds. So we want to know what is the weight of steel that you can use, pull with that winch. Okay? Well, what is pulling against you? If that was ice, okay, but you got friction, and friction always resists the motion. Okay? So the frictional force that's resisting the motion, that's going to equal this here. So this frictional force, F due to kinetic friction, that's going to be your 450 pounds. Okay? Now, what is that force due to kinetic friction? Go back to that same formula we had before. Does anyone remember the page? Oh, there it is. I got it. On page 132, that force due to, I put little f, they use capital F. And this is kinetic friction. They just use F sub F. And mu sub, okay? And the normal force, guess what? That's the weight. The normal force is equal to the weight. F sub W is equal to N. Because it's not going into the floor or off the floor, that's your normal force. So this is equal to 450 pounds, that's the frictional force, has to equal your weight, F sub W, times your coefficient of kinetic friction, 0.30, mu sub K. I should have put mu sub K in front, but it doesn't matter. And how do you get the weight? Multiply? It doesn't ask for mass. It asks for weight.
Don't you have to divide the 4, no, because 0.30, well, 450 divided by 0.3.
Exactly. And that should give you a pretty big number. I won't give you an answer. Okay.
What you got? So this ain't gonna be like the other Elsa one we had. What you had? I don't know. The first one was something different. No, it's not. You know, the other one we changed it around the division. That's what's happening.
Okay.
But does
Well,
it
you
say
see,
pounds or does it
okay. You see this formula here? That's right, isn't it? The F sub K is that exactly equals what you're pulling with. Okay. So this is equal to F sub W. That's the weight times your coefficient of friction. Okay? This is what you're looking for. So you need to solve for that. How do you solve for it? Well, this is multiplied here, so you undo multiplication by dividing. Divide by it here, but you have to divide the other side, 0.30. And that will give you FW, the weight. Okay.
You know something? If you divide that 450 by the 1500, you get the answer. It's one because it gave me 0.3. Don't check this how much you want.
Okay.
That's right. What did you do? I just did the 450 divided by. Come on, after you did
Okay. Now, notice they didn't put a bar over this, so how many digits is that?
No, they didn't put a bar,
So that's only 2. 4 and the 5 are the only significant digits. If they put a bar, that would make it 3. Okay? This one had, that first 0 doesn't mean anything, that's just a placeholder. But the one after the 3 does count. You don't have to put a bar after a decimal. Any 0 at the end of a number after a decimal is significant. You wouldn't have written it down if it wasn't. Okay? So this has 2. Okay? So your answer should only be 2 significant digits, and you have 2. There's some extra zeros there. Don't put any bars over any of them. Okay? Huh? Yeah, you put the zeros there. They're placeholders, but you don't put a bar over any of them. The 1, 5 are your 2 significant digits. The answer is in pounds, yeah. Yeah, because your weight was in pounds, or your number 5. Okay. Yeah, that's exactly what you do. But you have to decide ahead of time. Again, draw a picture. Anything to the right is going to be? No. Signage. If you have a number line there, and here's your 0, anything to the right is? Positive. Anything to the left is? Negative. Okay? So you just write down what it reads in. It's basically just adding sign numbers. Yeah? The sign numbers. Okay? A negative is going to be a negative. And okay. Yeah. Okay. You know what it turns out to be? You're playing tug of war.
Yeah.
That's exactly what you're doing. Team to the right is pulling with those forces. The team to the left is pulling with that. The problem is you got more to the right than you do. No, you got 2 to the left and 2. No. Oh, nope. You got. I can't read. 1 to the left and 3. No, 2 to the left and 3 to the right. Okay.
So you're going to have what, different answers on each one?
No. Okay. 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 Here's the easy way to do it. Write down, anytime you see left, put a negative. Anytime you see right, leave it a positive, right? And you're adding in all those up. If it's positive, you put a plus sign. If it's negative, okay. The easy way to do it is add all your pluses, add all your minuses, and then take the difference between the 2 and give the sign of the larger number, right?
Now, quick question. On number 8,
Okay.
I did my problem, but
Right.
it's only 2 or 3.
3 significant digits.
So my answer needs to only be 3.
3 significant digits, yeah. So count the first 3 digits you see, look to the right. If that's 5 or greater, increase the one that you stopped at, the 3rd digit. If it's less than it, then change everything to the right. I mean, depends on how many digits you got.
I have 4.
4 digits. So then you'll be something like 2450, 1780. If you have 4 digits, the only 3 will be significant, so the last is going to be a 0 with no bar over it. Okay? How are we doing? Good. Okay.
I'm not sure if I want to turn it in yet, but I need
Well,
to.
you don't have to turn it in until you feel comfortable. Is this making sense?
Yeah.
Good. Do I need to leave it recording any longer?
No.
Okay, I'll go and turn it off.